And I was trying to put up a little explanation on the question we just talked about, just had. We were given that for a characteristic X-ray of 57 AeV, what should be the least energy of the incident photon? A photon that has um, for if a photon has an energy of 2 keV, the best that can happen is the best that can happen to the atom is for this to be ejected. Is for this to be ejected. The electron here will be ejected. Okay, that's good. This is 1. This is 2. This is 12. This is 69. If you have the electron here, you have 2 keV, knocks it out, and nothing happens here. The electron has been removed. It will now begin to move with the incident with more the 1 keV additional energy, that will be the kinetic energy. So we are not going to have any characteristic energy, characteristic emission. But here, if we have an energy of 3 keV, if this one is knocked out, of course, this one can be knocked out also, but the energy will likely go here because this is the closest to it. It knocks out this one out. Then this one falls to fill this. This one is 2. This one falls in here to fill this one. We have characteristic energy of 2 minus 1, 1 keV. So with the 3 keV, the highest characteristic energy X-ray emission we can have is 1 with this keV. Likewise for this one, this is 2. If you have an energy of say 14 keV, this one can be knocked out. This one can be knocked out. If it is a knockout, we are going to have the characteristic energy emission, characteristic X-ray emission will now be 12 minus 10, 12 minus 2, which is a 10 keV. So we have 10 keV characteristic energy. So 14 wouldn't be enough to give us a 57 keV emission. But if we have something like 70 keV, 70 keV, of course, can knock this one out. If it knocks it out, we will have a vacancy here. It will not be filled with this electron from here. And evidently, apparently, we have an emission of 57 keV. So this is the least energy it must have. Or say this might not be the least, or we can have a 69.1. Or from a question, we have a 70. 70 is the closest to the answer. So 70 keV can actually give us a characteristic of 57. Of course, we have other characteristic X-ray. We have from here, because as this one goes down here, this one will come here, this one will come here. So we have so many characteristics. We have 1 keV characteristic. We have a 10 keV characteristic X-ray. We also have a 57 keV characteristic. So 70 is the least energy that the electron must have in order to have this characteristic X-ray emission. Just by the way, it's good we understand it's very well. So let's continue our screen sharing. Oh, no, 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 no. Oh, sorry. So that's that. So for 25, I think we should be able to finish before that time. 25. Which are the following instead of a polychromatic electrobeam?
Option B, sir.
Yeah, the second HBA is always greater than the first HBA. That's why we have the what's it called, the homogeneity coefficient less than 1, because homogeneity coefficient is in the first HBL over the second HBL. So because this leads to beam hardening. So 26. Yeah, this is the question. The number of pumping and photoelectric.
Hello, sir.
Okay.
Hello, sir.
Yeah.
On the previous question, sir.
Okay, let me go back. Okay.
When we see a question like this, okay, are we saying that it's only we are talking about the photon energy, not the intensity of that of the beam we are talking, because they are polychromatic. At first half value, a lot of will have been removed. We are now having more average photon energy, but the intensities of the beam has reduced.
Yes, the intensity has actually reduced. Yes, the intensity has reduced.
So when we see a question like this, so we are only focusing on the energy, average energy. We are not talking about the intensity of the beam again.
No, not the intensity. The intensity has got to do with the number of photons. This one is talking about the effective energy of the photons. Yes, the number of photons, that is the MA or the MAS. That is the MA, or that's the MA, that's the what's it called? The charge. The number of charge and the time. MAS. S. So MAS, they will actually give us about the number of photons, that's the intensity of the photon. But when you are talking about the energy, it is the HVL like this order. So the HVL is a measure of the average the effective energy of the beam, not the number of the beams. The number of the beams will be reduced as we bring in attenuators. The number of beams will be reduced, but the average energy of the beam will be increased. As the effective energy of the beam will be increased. Let's say you have 1,000 photons passing through a beam, passing through an attenuator. It will be reduced when at the other end. So that is why we have, of course, half value layer in a way. So half value layer is the amount of this thing that will reduce the stuff by half. The thickness of the material that will reduce the number of intense, that is the number of the photons. But the energy of the photon is a measure, is measured by the HVL value. I hope I'm making sense. The HVL is in the half value layer. It's an attenuator that will reduce the intensity of the radiation by 1/2. But that HVL also imposes an energy discrepancy on that system, on that attenuator, in the sense that the energy of the beam coming out from the other end will be increased. That is the effective energy, because more of the photons that are less energetic would have been attenuated by the beam. So essentially, we will now have more photons with average energy being increased. Is it okay?
Yes, sir. Yes, sir.
The first HBL they mean here and second HBL. They are talking about the same HBL. Assuming you have gotten the HBL of lead to be, for a particular energy, to be maybe 2 millimeter of lead at the HBL. They bring in the first HBL, 2 millimeter of lead. Another HBL, 2 millimeter of lead. Another HBL, 2 millimeter of lead. So the HBL is constant. So if you add one HBL here, you measure the intensity of beam, you measure the energy of the average energy of the beam. You're going to have maybe an average energy of say 60 keV. You put in that another same HVL, another millimeter of the same millimeter of lead like you use in the first one. You now measure the energy at this other end. You are going to find that the average energy will be increased, maybe to up to around 72 keV. So it is the HVL, it is the energy that is being measured. So the number of commuting and photon, okay, 26. And photon energy. And photon energy. Well, for this question, as from 25, 35, 45, 55 can be applicable. But for soft tissue, they have equal values at around the 25 keV. For soft tissue, they have equal values at 25 keV. But if you are looking at for very bonier tissue, you might be looking at 55 or so on and so forth. But for something like a water, of course, which is approximates the density of a soft tissue, the computing and photoelectric tissue, they are the same thing at 25. Of course, people, you wouldn't use a human being to begin to measure computing and photoelectric. They use water for that. And it was found that at 25 keV, these two contributors are the same. The same. So that was why the earlier question, when we had 100 keV, which is the dominant distance. Immediately you cross the 25 to 30 keV mark, something now begins to predominate. Thus, and the photoelectric effect will now begin to reduce at around 25. They are basically 50% contribution each. At 27, the mass photoelectric effect, blah, blah, blah. So what's our answer here? What's our answer? We do a little bit of mathematics here. Okay, let's go over to the board. But before then, I need to get the values. 12. 12 is 12 keV is 4
Option B.
centimeters squared per pound. Okay. Option B. Then for 120, 120
Option B.
Option B. Okay, let's go. Let's stop the share and face our board. So the mass photoelectric effect, blah blah blah, the tissue is 4 centimeters squared per gram at 12 keV. What would be that at 120 keV? Which not for the photoelectric effect. The contribution of photoelectric effect, let me indicate, represent that by P, is directly proportional to Z over E everything Q. I think it's Z raised to power 3, E raised to power 3. Very, very dependent on these entities, the atomic number and then Z. Directly proportional anyway. Some other. So if we now, we can bring in a proportionality of constants, which is K, now the Z3 over E3. So therefore, we can say, okay, we are looking at K and we are not looking at energy. Okay, energy is there. We are looking for the same Z. So we might forget about this E for Z. We are looking at the same Z. So Z and the other constant have now become a constant, the new constant. So at a particular Z. So we can now have E raised to power 3 is or K, and say our K is the photoelectric effect multiplied by energy raised to power 3. So what this means is that E1 cube is equal to P2 cube is equal to P3 E3 cube, and so on and so forth. So this relationship holds because it's a constant. The sum of the product of this will always be the same thing. As you and this one, in fact, the two products have to be the same thing. They have to give us a constant. They are indirectly proportional. P and then E. So at 12 keV, the photoelectric effect was 4. Photoelectric effect contribution was 4. I mean, the mass attenuation coefficient contributed by photoelectric effect is 4 centimeters squared per gram. This is the photoelectric mass attenuation coefficient. So we have that to be 4. 4 multiplied by 4 multiplied by 12 squared is the same thing as should be the same thing as what we are looking for now, multiplied by the energy, which is 120 raised to power 3. So we are now going to have P2 will now be equal to 4 times 12 raised to power 3 over 120 raised to power 3. We shouldn't bother ourselves with a calculator. We have 4 times 12 raised to power 3 over, this is something at 12 raised to power 3 times 10 raised to power 3. 12 times 10 is 120. So we now have that. So we are left with 4 over 10 raised to power 3, which is 4 over 1,000. So that gives us a 0.004 centimeter squared per gram. So it's just after when we see a question like this, all we need to do is since this is inversely proportional to the energy all we need to do, we look at how these have varied, how they have varied. 12 over 10, 12 over 120 is 1 over 10. So this one has to be affected since photoelectric mass this of the photoelectric effect is C raised to power 3. So this one we have to be affected. So just multiply this by that to get our value since they are inversely proportional. If it had been with Z, if it had been with Z with the atomic number, it should have been times 1,000 because it is directly proportional to Z. The photoelectric contribution is directly proportional to Z, but inversely proportional to the energy. So we continue with that. So 0.004 centimeters squared per gram. So 28. We can make it, we should be able to finish everything. So constant interaction does what?
Visa.
Constant interaction change come to interactions, change the direction of the incident photon. Of course, yeah. Change the direction of the incident. That's straight. It decreases
Hello,
with
sir.
energy.
What is option A?
Option A is wrong. It decreases with
It's
energy.
wrong, yes.
As the energy increases, come-to interaction decreases.
Decreases, yes.
Photoelectric effect also decreases. Rayleigh scattering also decreases. But pair production increases. Immediately you get to the mark of 1.02 megaelectron volt. Pair production will now consistently continue to increase. So 29.
I think, hello, sir.
Okay.
Okay, maybe but in relation to photoelectric effect and the Compton,
Okay.
the energy relation, one is A super 3 and one is just directly
proportional. Yes.
Inversely proportional.
Yes, directly inverse. I mean, inversely proportional to the first order, kind of. Yes, Compton effect is directly proportional to 1 over E. Did you get that? It's directly proportional to 1 over E. Or I say inversely proportional to E. Whereas photoelectric effect is inversely proportional to 1 to E cube, E raised to power 3.
Yes, sir.
So it
Yes,
Compton photoelectric is heavily influenced by energy change, and of course also by the Z change in Z. 29.
B.
Okay, B, that's straight 1, 3. It has a high atomic number. It also has low mass accumulation coefficient and tissue. Okay, those are 30. If the photoelectric mass accumulation coefficient is 25, what is it at 50? Still the same thing. We have 25 over 50 is 1 over 2. So you just 1 over 2 raised to power 3 is 1 over 8. As I multiply this by 1 over 8. Multiply it by 1 over 8. So we have our answer. Whatever that gives us is our answer. I hope we are there. And if we have any issue with that, we can now do a back of the envelope calculation. Just like we did for the other one. 25 over 50 is 1 over 2, 1/2. But then everything raised to power 3 is 1 over 8. Multiply 1 over 8 by this. Let's just see 8 here, 2, 8 here, 16, 18, 19, 8.
A 0.03.
Okay, 0.03. Yeah, 0.03. In diagnostic energy range, the atomic number of an observer changes from Z equals to 20 to Z equals to 40. In material 2, the mass accumulation coefficient of material 2 is dash.
It should be less. It should be less. It should be less than. It should be greater than that in 1.
Greater than.
Yes, A.
Yeah, it should be greater than. Because the material will now encounter more number of atoms.
Yes,
so it will be greater in the number of photons per gram. Okay, I still want that question to display. The number of photons per gram absorbed by photoelectric effect in material 1 is dash times as many relative to material 2. Remember this time around, we're not talking of energy. We are assuming the energy is a constant. So what will happen to the number of photons per gram absorbed by the material by the photoelectric effect in material 1 to that of material 2?
0.5, sir. A?
0.5.
Half of it.
Is seriously, it can never be 0.5 because we are talking about photoelectric effect. Yeah, something should be raised to power 3. It's either 20 over 40, which is half, raised to power 3, or which will give us 1 over 8, or something 40 over 20, which is 2 raised to power. So the answer.
So that's 2 times. That should be.
Yeah, the
2
answer
raised to
should
power
3.
3.
The answer
Yes.
should be something
D.
8 or 0.0.
8, sir.
But I don't think it's 8. Let me see. I don't think it's 8.
And it's supposed to.
It's supposed to be 1 over 8. I don't think it's 8. 8 is here, but it shouldn't be 8. Because we are talking of material 1, which has a lesser z. So material 2 has 2 times the number of z material 1 has. Did you get it?
Yes, sir. The attenuation should be greater.
Yeah.
The number of photons gram that is being absorbed should be greater than that in 1.
Yeah, it should be greater than that in 1.
Should be times 8 of it. Yes, sir.
So it should be
I think 8 is correct, sir.
So it's a relative to material. Okay, in 1 relative to material 2. Okay. No. Material 1 is 8 times. Okay, that's correct. Okay, that's correct. In 2 is greater in 2. So the material in 1 relative to that in 2 is 8 times.
Yes, sir.
Okay, 33. This one is a good one also. There's a 75% chance of a photon in a monogenetic beam being attenuated by 2 millimeter length. What is the Higgs?
I think B, sir.
B. Okay. Why B? How B?
Well, sir, the formula I used was this HVL equals to 0.693 over the attenuation coefficient.
Okay.
And since they gave me 75% chance, so and it's mono energetic, okay, that should be 0.5 I thought I did one with rule like that. I got 0.9 something and I approximated it to 1.
Okay.
So I don't know whether there's a better way out.
It's okay. That's very okay. I love that. This is not a Viber. It's not an aura. Okay, why did you think this? Love that. Blah, blah, stuff. So let's see. Let me quickly screen and stop this and share. And then go to the board. We have a 75% chance. What is the question? 75% chance that it will be transmitted or attenuated. Okay. Attenuation, and you have a 2 millimeter length. What's the HGL? And there are so many few approaches we can go here. We can use the first approach, which is n over n in blah 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 equal to. So this is can be taken as a HGL. If we get this, 75% attenuation. So it means we have 75% here, 75 over 100 equal to this, blah, blah, blah. This one is times 2 millimeter. At the end of the day, when we have this, we know that this is equal to 0.693 over HDL. But if we use this formula is only applicable if we know the thickness. If the thickness is very, very small. But how small is 2 millimeter, which we don't know. We don't know how 2 millimeter is small, how small 2 millimeter is. So to avoid that problem, running into the problem of distinction between clarity of the smallness of the observer, it is best to use the general equation, the most general equation, which is calculus and base. That is n equals n naught epsilon is. So for that, 75% attenuated. This n is the number transmitted. This n is the number transmitted. So it means n over n naught should be equal to n. So if 75% is attenuated, it means only 25% wasn't transmitted. So it means this n over n naught will now be at 25%. 25 over 100 equals epsilon. Our HDN is now 2 millimeters. Let's take it for that. So we have a minus, sorry. So we have 1 over 4. Okay, 0.25 will now be epsilon this times 2. 2 epsilon 2 mu. So you can somebody help us with the what's it called? The natural logarithm of this. The natural logarithm of this. The natural logarithm of this one is in 0.25 to be equal to the natural logarithm of the whole of this will give us minus 2 mu. So what's the natural logarithm of 0.25? I'm going to use a calculator quickly. I have a calculator on my screen. Running out of time. Natural logarithm of 0.25 minus 1.39. So this minus 1.39 is minus 2 mu. So we now have mu, will be minus 1.39, so it's 1.39 over 2. And our mu, we should remember, is 0.693 over HDR. So we have to have a bit now equal to 1.39 over 2. At the end of the day, we now have a HDR to be equal to 2 times 0.693 over 1.39. 1.39. So that gives us 0.997. 0.997. After which approximately 1. And we're talking in millimeter. 1 millimeter. So it's approximately, the HBI is approximately 1 millimeter of lead. Approximately 1 millimeter of lead. But there is a quick way of going through this. There's a quick way of looking at this. Of course, this is the overall, this is the most correct way of solving this equation. But if you look at the question, at times, some of these questions, they are designed in a way that you don't need to use any calculator. Most times, MCQs are designed so that we don't have a need of a calculator. 75% was attenuated. It means we have 75% attenuated. It means 25% was transmitted by 2 millimeters of lead. So what would have been transmitted 1 millimeter of lead? I mean, what would have been transmitted 50%? Anything that transmits 50% is the HBL. Any thickness of material that transmits 50% is the HBL. So what can we draw about from that? It's just a very, very rough idea of doing it. 25% was, 25% was transmitted by 1 millimeter. what would have transmitted 50%? If you reduce this by one half, if you reduce this one by half, by one half, which is 1 millimeter, if you reduce it by 1 millimeter, it is going to transmit 50%. If you transmit 50%, then this is a HVL 1 millimeter. So we move on. Did you get that?
Sir, please, can you come again on that? I love it.
75% was attenuated by whatever of lead was attenuated by the whatever by the attenuator. So it means 25% was transmitted, 5% was attenuated, was absorbed. So leaving just 25% of the X-ray photons to pass through. That is what the question then gave us. But HVL, we know it to be that amount of attenuator that we transmit or that will absorb 50%. Whether absorb or transmit, if we absorb 50%, it means that 50% was transmitted. So 25% was transmitted. For 50% to be transmitted, it means we have to reduce this one by one half, because 50% just a half, it's just 2 times of 25%. So the more the lesser the attenuator, the more the transmission, the more the number of photons that will be transmitted. So if 50% was transmitted, it means that 50% was absorbed. And what is our HVL? Our HVL is just the amount of attenuator, the thickness of an attenuator that will absorb 50% of the beam. So 50% was absorbed here, 50% was given up. So 1 millimeter is our HVL.
Yes, thank you, sir.
They get the logic. Okay, you're welcome. We have 10 minutes. Oh my God. Oh. Okay. So 1 millimeter should be an answer. So Compton effect, Compton scattering 34.
B.
Outer shell electron, yes. 35, photoelectric effect.
B.
35, photoelectric absorption.
I think A.
I don't think it is A.
I think it's B. It's D. I don't know.
It's not complete
like D.
absorption.
Option D.